everybody, I'm going to talk about integration and multiplicity and NMR in this video. So integration and multiplicity, we want to keep very clearly in mind that these are both only for proton NMR. Okay, we're not going to see integration or multiplicity in a carbon NMR. So this is an NMR for proton only skill or technique that we're going to use here. Okay, so integration and multiplicity are commonly confused. So I'm putting them in the same video in the hopes that we can make sure that by the end of it, we have it clear which one is which. So integration is going to be how many protons make up each peak. Okay, and so what we're thinking about here is we're really interested in seeing those equivalent type of situations where if we have a lot of symmetry going on and we have, you know, like two CH2s that are in exact same environments and they're equivalent. If you haven't watched the equivalent video, I'd watch that first. So if they are equivalent, then they will be showing up in the same peak, and that peak will just be larger and integrate to a bigger number, indicating like, hey, I've got 4 protons in this peak instead of just 2. Okay, so that's what we want to look at. It is determined by a ratio and comparing them to other peaks. So integral, right, is just the area under a curve. So we have software that determines like what is the area under each peak, and then it compares that to the area under other peaks. So it's really just a ratio of like a 1 to 1 to 2 to 3, like that's what it's going to spit out. So if you've got a ratio like that, you have to be sure that you're not being tricked by somebody and it's not actually giving you the full proton count. It could be like halved instead, right? And I'll show you an example of that as well. All right, so first up, let's look at this one. So the very first thing you need to do to figure out integration is we want to think about the different environments that are present in this molecule. Okay, so just like we did in the equivalence video, we're going to think about this is going to be one proton environment, which is different from the B proton environment. This carbon has no protons on it, so that's not going to show up. But then all of the methyls on this tert-butyl group are going to be the same. Okay, so basically what we have here is we've got these 3 H's here, these 2, and then, I did not do myself any favors with those C's. Let me move those. Okay, and then I've got those protons, C, 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 and we're just going to move A and B closer to the actual H's. Okay, so the A's, those 3 H's are the same, the B, the 2 H's, C, those 9 H's are all the same. Okay, so what we're looking at here is if I've got 3 proton peaks here, right, then I'm looking at the A peak is going to integrate to 3 H's. The B peak is going to integrate to 2. And the C peak is going to integrate to 9 H's. Okay, so those would be our integrations. So it's going to be like a 3 to 2 to 9 ratio. So the thing to keep in mind here is making sure that you can actually identify what is the integration on the NMR. There's a couple places it's going to be. So you'll either have like your peak, and then in a little bracket, you'll have like 3, or you might see it, your peak, and then a little bracket, and then the 3. You might have your peak. You might see a weird little like integral sign in a 3. So there's a couple different places that you're going to want to look for those integration values. Most of the time they're going to be down below, but it kind of depends. Okay, and as you get used to looking at NMRs, you'll be able to pick up where they are a little bit easier. All right, so let's look at this one. So for this, we, again, first look for symmetry. So I do have a plane of symmetry right down that oxygen. So I'm going to have my H's. I'll draw those in. Okay, so I'm going to have A and B. So my A proton, I'm going to have 2 proton peaks total. So when I'm looking at this, A, it's really easy if all you have drawn out is this. It's really easy to say like, oh, well, A's in it integrate to 2. But keep in mind that over here on this side, we have another 2 protons that are in the exact same environment as that A. They are also A. So they are going to be 4 protons total. Okay. Your B is going to be a total of 6 because it's this 3 plus the other 3 over here. Let me draw those out. Is going to be 6H. Okay. So this is a situation where if you see a proton peak and it integrates to 4, you need to think really carefully about what that 4 could mean. Okay. Because that is 4 individual protons that are in identical environments. So unless it's methane, where it's just CH4, you got to have something else going on symmetry-wise. Okay, it's just not possible to have 4 protons around 1 carbon and have it still be connected to another molecule. So when you're looking at this, that 4, I would go towards the simplest route always and say like, that's probably a 2 + 2 situation. So I probably have a CH2 and then another CH2 just like it somewhere else in the molecule. And that's the kind of logic processes that we want to go through. And the other way that you might see this, you might see it listed as 2H and 3H, right? Because if we're thinking about ratios and kind of like the simplest ratio that you can present, 4 to 6 is a really good representation of this molecule, but 2 to 3 also does the same thing. It just means that, yeah, this has to be doubled, that has to be doubled, but that's one way that sometimes you'll see people present it, especially if they're trying to trip you up. I will not try to do that, but it's just something to watch out for, okay? So it can boil down to a simplified ratio like that. Alrighty, so that's integration. So let's take a look at multiplicity. So I just want to say again, integration, how many protons make up that particular peak? Okay, that's all we're looking at. Alrighty, so let's look at multiplicity. So multiplicity, and I will say this is also called splitting or coupling. Okay, a bunch of different ways that you can say it. This is again a proton NMR only. So there's a lot that you can get out of a proton NMR. The carbon NMRs are helpful, but it's just different. You can get more information, I would say, out of a proton. So multiplicity is how many neighboring protons are present. Okay, we're looking for neighboring protons. It has nothing to do with the protons actually making the peak. Okay, it only has to do with the neighbors that are nearby. So neighboring is going to be the H's on adjacent carbon atoms. Okay, so let's look at a situation here where we just have a CH2. Okay, so if I'm looking at this, These are going to be the ones that I'm looking at for my peak. Okay, those are going to be the ones that I'm using as like my, this is my peak. Okay, so the integration would be 2. Because there's 2 protons making that peak. And then if I look to my adjacent carbon atoms or my attached carbon atoms, these are my neighbors. And I've got 4 neighbors here. Okay, so that's what we're looking at. If we're looking at these H's, we want to look at the carbons attached and how many H's are on those carbons. All right. So when we're looking for multiplicity, we're looking for the number of neighbors plus 1 is going to be our multiplicity for that peak. Okay, this is also called the n+1 rule. So you'll see it as n+1 quite a bit. The last important note about multiplicity, equivalent protons don't split each other. Okay, so you cannot be a neighbor if you're the exact same person. Okay, you can't be a neighbor if you're yourself. So that's what we're looking for, making sure we don't count anything that's equivalent as a neighbor. Okay, so let's look at some of the peaks that we're going to see. So the multiplicity, and I'm going to put this up here. Let me scoot this down just slightly. I just have one little thing that I want to add. Okay, so the multiplicity is going to define the peak shape. Okay, integration is like the peak size, right? The area, but the multiplicity is going to be the shape of the peak. So it's something that you visually determine. It's not a number that's written down for you. Okay, so let's look at a few examples. So if we have a situation, we have 0 neighbors. Okay, that's going to be 0 plus 1 equals 1. Okay, that's going to give us a singlet. If I could just draw straight, that'd be awesome. Okay, singlet, it's going to have the 1 maxima on it. Okay, if I have 1 neighbor, that's going to be 1 plus 1 equals 2. That's going to give me a doublet. Also, singlet is going to be a small s. Little d. Okay, 2 neighbors. Two plus 1 equals 3. So that's going to give us a triplet. Little t. 3 neighbors. 3 plus 1 equals 4. That's going to be a quartet. Let me try that again, actually. It's going to be little q. If I've got 4 neighbors, 4 plus 1 equals 5. That's going to give me a pentet. which I really have to pay attention for this one. Just count 1, 2, 3, 4, 5. Yes, okay. 4, 1, 2, 3, 1, 2. All right, so this is a pentet, and that's going to be little p. You'll see that less frequently though. Okay, so that's what I mean by peak shape. It's the difference between having these different shapes. These are all one peak only. Okay, so this is a single proton environment. It's just showing you that whatever protons are making up that peak, they have one neighbor. Okay, so that's the kind of thing that we're looking at here. So let's look at an example. Oops, helps if I have the pen out. And the really cool thing about these splittings is that it actually comes from like Fibonacci's triangle in terms of what the shape of the peaks are, where you've got like 1 and then 1, 1 of equal size, and then 1, 2, 1, where this is about twice the size of the little ones, and then it's really cool. So that's kind of how these got developed. It's pretty neat though. Math is fun. All right, let me getting off track here. Okay, so let's look at this compound. So first thing I'm going to do is I'm going to draw in all the H's. And then we need to figure out how many peaks we're going to have, how many environments. Okay, and if you're struggling with identifying like planes of symmetry, use your model kit. Your model kit's still going to be your best friend for this. It's going to help a lot, I promise. All right, so if I have this situation and I'm looking for, we're going to do integration and we're going to do multiplicity here. So if we're looking at that, first things first, all of those H's are going to be one environment. These H's are one environment. We need to look carefully here for these two because they're both 2CH2s, but because we don't have a plane of symmetry here, because this is the isobutyl and that's an ethyl group, we do not have equivalent proton environments here. So this is going to be C. We do have a plane of symmetry down here. If you build a model, it's easier to see, I promise. So I would have D and then E. Okay, so let's make a little table here. We're going to make a, let's say, okay, proton environment. Have number of neighbors. Peak shape. And the integration. All right, so we've got A, B, C, D, and E. Okay, so A, let's do integration first because that's easy. So in this case, we only have one A environment. We have 3 H's in that environment, so that integration is going to be 3. Okay, the number of neighbors, we go A H's are on this carbon. That carbon is attached to this carbon, which has 2 H's on it. That's going to be 2 neighbors. 2 plus 1 is 3. So that's going to be a triplet. Okay, so we've got our little triplet there. So all in all, it's going to look like a triplet, and then you're going to have a little 300, as in it integrates to 3. Okay, so that's what we're looking at. All right, so B, again, let's do integration first. I should just switch this, but whatever. So integration first, B has 2 protons in that environment. 2H. The number of neighbors it has, I've got neighbors over here. So things are neighbors to each other, right? So if we're looking at B, we're looking at this carbon. It's attached to that carbon that has the 3 H's. This carbon has no H's. Okay, so we need to make sure we go both ways. So in this case, I've got 3 neighbors. So then 3 plus 1 equals 4, which is going to be our quartet. So it's, oops, going to be our quartet. And I'm going to erase this 3 so that it doesn't confuse people watching the video or looking at the PDF. All right, so then let's move on to C. So again, C is a CH2, so we've got an integration of 2. For neighbors, we're looking at this carbon. That carbon has no H's. That carbon has 1 H. So we're got 1 neighbor, 1 plus 1 equals 2. So that's going to be a doublet. So it'll look like that. And then D is 1 H in that environment. So now D, if I'm looking at neighbors here, I'm looking at this carbon, I need to go up here. I need to go down here. And I need to go over here. Okay, so I need to count all of its neighbors. So I've got a total of 1, 2, 3, 4, 5, 6, 7, 8 neighbors. 8. So then 8 plus 1 equals 9. So this is going to be a tough one for me to draw. I'm going to try to keep it all there. So that is a nonet. Okay, non as in 9. So I'm going to count out loud to 9 while I do this. 1, 2, 3, 4, 5. It's going to look something like that. Okay, so what you want to keep in mind here is a lot of times if you see something like this, sometimes the little edge ones will almost be like hidden in the baseline. They're so tiny because that splitting gets so fine. So what you want to keep in mind is just making sure that if you see something like this, you should tell yourself that thing's got a lot of neighbors. And like sometimes that's all you need to solve the puzzle. Okay. All right. So then let's look at E. So E is 2 methyls. So it integrates to 6H. Okay. In terms of neighbors, we only need to look at one of these to determine how many neighbors because they should have the same number of neighbors because they are equivalent. So for this one, all we need to do is look down and our only neighbor is D. Okay, so we've got 1 neighbor. 1 plus 1 equals 2. So that's going to be a doublet. It's going to be a great big doublet though because it integrates to 6. All right, so as always, let me know if you have any questions. Hopefully this kind of gets you on track with your NMR stuff. I'll be doing another video kind of showing how I go through an NMR process in terms of, you know, given blank copies of an NMR and then figuring out how to solve it. I'll be showing you kind of how I go through that. I kind of hop around a little bit, so I'll just show you what that looks like. But this should be a good start to kind of get you going in figuring out some of those NMR things. So as always, have a good one and I'll see y'all later.